Hello 3C class and welcome to the video lectures on section 15.4, which are applications of double integrals. The first thing I need to do is introduce you to the notion of a lamina. A lamina is just an idealized thin object, which means we're going to treat it as two-dimensional. Now here I have a model of lamina. This looks kind of like a piece of paper, okay? When I have a piece of paper, I do think of it as a two-dimensional object. I can talk about the area of this piece of paper. I would very rarely talk about the volume. But technically there is some thickness to this, so this is a three-dimensional object with some actual volume to it. I can't actually bring in a real lamina because if it had absolutely no thickness to it, I wouldn't be able to touch it or pick it up or carry it, okay? So it's sort of a mathematical abstraction, but we can use that idea to treat something that's very, very thin as if it's two-dimensional. Eventually we'll be able to work with curved surfaces, so curved laminas. For this section, all of our laminas are going to be flat, so they're just going to be subsets of the xy plane. Okay. Now, if I have a homogeneous lamina, that means that the mass is evenly distributed. So, pieces of paper tend to be homogeneous. If I were to cut this in half, I would have just as much mass in the left half as I did in the right half, okay? But not all laminas come that way. Some of them are non-homogeneous, so that parts of it are more massive than others. You could imagine if there's a whole lot more mass right there than there is here, okay? That would be an example of a non-homogeneous lamina if this were mass rather than just marker ink. Okay, when we have a homogeneous lamina, we can define the density to just be the mass divided by the area. Okay. So it tells us how much stuff there is per square inch or per square centimeter or something like that. If I have a non-homogeneous lamina, we're going to have rho of xy, which is going to be our density function. It's going to do the same thing that density does, which is basically tell us how much mass there is per unit area, except if it varies, we need to know where we are as we're talking about that. Now, of course, that's a bit of a dilemma because an individual point won't have any mass or any area because points are infinitesimally small. But that's okay. We simply define this as a limit as, I'll just write as delta A goes to 0 of delta M over delta A. So I take the ratio of mass per area. I would, let's say I wanted to know what the density function is right there. I would take a little piece of the lamina, and I could now measure the mass of that piece and the area of that piece to create this ratio. And then I would take the limit as I shrunk the area to 0. Just need to put a little asterisk here, because I could, in theory, shrink the area to 0 by just making this really short, but keeping it fairly long. That's not good enough. So I'm just going to say all dimensions have to go to 0. So if it's a rectangular piece, the length and the width would both shrink to 0, and that limiting factor is what we call our density function. Okay. I can do the same thing if I have charge distributed on a lamina. I could have charge density then, and we usually use a Greek letter of a sigma for that. So as soon as I've erased the board, I will show you what that looks like. So charge density would be sigma of xy. That's a lowercase sigma. We use the uppercase when we want to add things up. And this is just going to be the limit, again, as delta A goes to 0, making sure that all dimensions shrink to 0 of the charge over the area. Okay, so one application of double integrals is this. Let's suppose that I have a density function rho of xy equals xy, and my lamina happens to be the quarter of the unit disk that's located in quadrant 1. Okay. So this would be bounded by the x-axis, the y-axis, and the unit circle. And we're talking about that region having this density function. Okay. If I were to, so I'm going to call that region D, if I were to integrate over D, rho of xy dA, and think about what that means. Well, anytime I want to figure out what an integral means, I'm going to remember that we got this by looking at a Riemann sum, where we were multiplying a representative value of this function by a small change in area. And if this was constant, if we were working with a homogeneous lamina, then I could actually just multiply this by the total area and get the same thing. It's when something is changing that we would usually use in a multiplication problem. When it's changing, we replace multiplication with integration. So if I look at this, this was mass per unit area. I'm integrating with respect to area. So what I'm getting is what I would get if I multiplied mass per area times area, which is just mass. That's a nifty way of figuring out what an integral is actually calculating. You just say, if this was constant, what would I get if I multiplied what this gives me times what this represents? And that will always give you the meaning of the integral. So in a similar way, if I were integrating a charge density, that would be charge per area times area. That would give me the total charge that was distributed across the lamina. Okay, so let's actually do this problem and calculate the mass of this particular object. So let's see, if this is my lamina, I think I want to work in polar coordinates. Okay. So if we're working in polar coordinates, and this was the unit disk, I know that my theta will be going from 0 just to pi over 2, so that I just get the portion that's in quadrant 1, and theta is going from 0 to 1. Then my density function was xy. I'll write that in terms of my polar coordinates, so that's r cosine theta, r sine theta. And then dA, don't forget there's an extra r, dr d theta. Okay. So that's going to be the integral from 0 to pi over 2, integral from 0 to 1 of r cubed cosine theta sine theta dr d theta. I'm in the habit of always setting up my polar integrals dr d theta. In this case, it doesn't matter because I've got constant limits of integration for everything, so I could Fubiniize if I wanted to. But remember, if we do have functions, it's usually going to be r as a function of theta. Okay, so let's see. This is the integral from 0 to pi over 2 of r to the 4th over 4 evaluated between 1 and 0, and then I still have times cosine theta, sine theta, d theta. So when I evaluate this, that's going to give me 1/4 minus 0. That's just 1/4. I'm going to factor that out. You get 1/4, the integral from 0 to pi over 2 of cosine of theta times sine of theta d theta. I'm going to do a quick u sub, though I'm going to give myself some space in which to do it. So I'm going to let u equal sine theta. That way du is cosine theta d theta. So this bit becomes my du. We're just integrating u, but we're going then from sine of 0, we still got that 1/4, sine of 0 is 0, to sine of pi over 2 is 1, and we're integrating u du. So That's 1/4 u squared over 2 evaluated between 1 and 0. That's going to be 1/4 times 1/2 minus 0, which is going to give us 1/8. Now, I hadn't given you any units for this density function, but it would be whatever units we were using for mass. If we're finding mass, it better be positive. That's one of those quantities that you can't have a negative value for. All right, excellent. Back in a moment.